it's me, Mrs. Duncan again, here to teach you another lesson of exciting online chemistry. I've got to be honest, I was really hoping we would be back in school by this point, and I could teach you this unit in person, but unfortunately that is not the case, so we'll at least start our next unit online and see where it goes from there. Okay, so let me pull up my PowerPoint. So this unit that we're going to start today is called Kinetics, and there's actually a follow-up part, which is called Kinetics and Equilibrium, but we're going to handle the kinetics part first. And if you think about the word kinetic, like kinetic energy, hopefully that triggers the memory that kinetics refers to motion. In particular, kinetic energy comes from the motion of the particles in a sample of matter. And that's a lot of what we're going to talk about today, how the motion of the particles in a given chemical reaction lead to collisions between them. So today we're going to talk about when reactant molecules collide and how that basically affects the rate of a chemical reaction. So before we get into all this diagram is awesome because it gives a basic idea about what happens during any given chemical reaction. So basically, you've got some reactant molecules. This is actually methane, it's natural gas, and these are some molecules of oxygen. Methane is flammable, it catches on fire, it combusts. But the point is, if you want to react a methane molecule with some oxygen molecules, the first step is you need to break the bonds in between those reactant molecules. So basically, you go from here, where you have all the molecules, the atoms are bonded together, to right here, a state where after you break the bonds between the atoms, now those atoms are free, at least very briefly, momentarily, and they can then rearrange themselves to form new products. So you break the bonds in your reactants, which allows you to basically rearrange them to form new substances, new products. So what we're going to talk about today is collision theory and how basically in order for reactant molecules to react with one another, they must collide. And the reason that these molecules must collide is there's a really big important step that happens. I'm going to back up for a second. That's this step, where when they collide together, they break the bonds between them. So if these molecules collided, each of these bonds would break, which would ultimately allow us to form our products. So the key is this. Molecules collide all the time. If you think about when you inhale and you exhale, when you exhale or inhale, the molecules that are involved in that process are colliding with one another. But it's not like you have explosions going on in your mouth when you're breathing, or at least I hope not. And that's because every time molecules collide, they don't always react with one another. So there's two types of collisions. There's effective collisions, where when you have your reactant molecules collide together, they do so in a way that the bonds between them break and new products are formed. But we also have ineffective collisions. So this is when, your reactant molecules collide with one another, but for some reason, which we're about to get into, when they collide, they don't break the bonds that hold them together, and you actually don't make any new products. There's no reaction that occurs. So in this case, that NO molecule and O3 molecule maintain their identity because they did not collide in an effective way, thus no new products were created. Okay, so in order to have a chemical reaction occur, your molecules have to collide, but they have to do so in an effective manner. So there's really two criteria that have to be met here. For effective collisions to occur, which produce new products, ones with different identities. First of all, when your reactant molecules collide, they have to collide with enough energy. Basically, that means they collide with enough force that the bonds between them break. So think of it as they have to hit each other hard enough to break the bonds between the atoms. The second criteria for an effective collision is known as proper orientation. So that means when two reactant molecules collide, they do so in a manner that they hit each other in the right spot. So these molecules here, they can collide pretty hard, hit each other pretty hard. But if they don't hit each other in the right spot, those bonds might break and you might not be able to produce a chemical reaction as a result. So if you'll notice, I know it's kind of hard to see, but in this situation, an ineffective collision versus this situation, what this diagram is trying to show is the orientation of these molecules when they collide is different. So basically, for effective collisions, they have to collide with enough energy, hit each other hard enough to break the bonds between the reactant molecules, and they have to collide with proper orientation, hit each other in the right spot. And that's what produces an effective collision. So now that we know that molecules have to collide with one another in order to react, and they have to do so with enough energy and the proper orientation, we're going to talk about 3 brief factors that affect the rate of a given chemical reaction. So basically, we'll talk about it in terms of things that can speed up a chemical reaction. Okay, the first thing that we're going to talk about is concentration. How many particles do you have that you're trying to react together? Because there's this whole guideline that's going to take over here. And that whole thought process, that whole guideline is the more collisions that you have between your reactant molecules, the more frequently they collide with each other, the faster the rate of the reaction. If you're in a situation where you have a lot of particles that you are trying to react, a high concentration of particles, the more particles you have in a given reaction system, the more frequently they would collide, thus the faster the reaction rate. So systems where you have higher concentration of particles have faster rates of reaction than systems where maybe that concentration is not that great. Because in this system right here, we would have fewer particles. They just simply wouldn't collide as frequently as the system over here to the right, which has more particles. So a real quick let's practice. Which of the following solutions would react the fastest with 1 molar HCl? If you notice, it's all the same thing. They're all NaOH. What's different about them is the concentration or the molarity of those NaOH solutions. The thought process is the more particles you have, the more collisions between them occur, thus the faster the rate of the reaction. You would want to go with choice D, which has the highest concentration of particles. There are more dissolved particles in the 1 molar NaOH solution than in the 0.75, 0.50, or 0.25 molar solution. So more particles, higher concentration equals faster rate of reaction. Okay, next up is temperature. So again, we're thinking about we want the most collisions possible. The more collisions or the more frequently reactant molecules collide, the faster that rate of reaction will go. You should know this, that as temperature increases, particles move faster and faster and faster. So higher temperatures lead to greater particle speed, the particles moving faster and faster. And as they move faster and faster, they collide more frequently with one another, which leads to a faster rate of reaction. So increasing temperature always increases the rate of a chemical reaction because you speed up the particles. The particles move faster as temperature is increased. Faster moving particles mean more collisions, which means the reaction moves more quickly. All right, last up, and then we'll do a quick let's practice. We're going to talk about surface area. So surface area is a little tricky to understand. Basically, surface area comes down to how many particles are available or readily available to react. So if I have, let's say this is a 1 gram cube of salt, okay, and I want to react it with whatever solution is in this beaker. If I put this whole cube of salt in this solution, it's really only the molecules that are exposed, that are on the outside of this cube, that are going to readily or quickly react with the solution in this beaker. The ones that are deep on the inside are not going to contact the solution and thus are not going to react. So a good way to increase your rate of reaction is to increase the surface area of your reactants. This can be done by crushing or grinding, if you have solid reactants, into a powder. Basically, if I take this 1 gram cube of sodium chloride salt and I crush it up and grind it into many, many small pieces, I'm going to expose the salt molecules that were trapped in the interior of that cube, so that when I put this in solution, this powder, more of those molecules are exposed and readily able to react with that solution. So, increasing surface area usually means grinding up your solid reactants into as fine of a powder as possible. More surface area, which is achieved through crushing or grinding, produces more exposed particles that are able to collide more frequently with whatever you're reacting it with. In this case, it's whatever is in this solution, which leads to an increased reaction rate. So greater surface area means more available particles, which means the faster the reaction goes. Okay, so that's kind of a visual of more surface area. So if these had the same mass, they're each 1 gram. There's more exposed particles in this situation available to react than there are in this situation. More particles, more frequent collisions, and greater rate of reaction. All right, I'm just about done. Let's try this. Let's practice. And then I suggest you look at the summary sheet that I have attached with this Google assignment, and then try the Google form, which is Kinetics Practice 1. All right, so let's read this. It says a student wishes to react solid zinc metal with hydrochloric acid, which is HCl, so zinc with hydrochloric acid. Which of the following conditions would produce the fastest rate of reaction, and explain your answer. So I'm actually going to go through it like down here, and then we'll figure out at A, B, C, D, which one of these is the best option. Let's talk about the sample size choice. So we basically have a zinc bar or a zinc powder that we can choose to react. We're going to go with the zinc powder if we want the fastest rate of reaction, because the powder has more, and I'm just going to abbreviate it as SA, surface area. The more surface area, the more particles are available to react, collide, and the faster the reaction will go. The concentration choice, we can react it with 1 molar or 5 molar hydrochloric acid. Going back to what we started with, the more particles you have available to react, the more collisions will occur and the faster the reaction rate will go. We're going to go with the 5 molar sample, the more concentrated sample, because that sample contains more particles, which can collide with each other, thus increase the rate of the reaction. Last up, we have a temperature choice. We can do this reaction at 100 degrees C or 20 degrees C. We're going to go with the 100 degrees C, the highest temperature, because at this temperature, the particles would move the fastest. As they move faster and faster and faster, they collide more frequently, and the rate of the reaction increases. So the best answer for this let's practice, which of the following would produce the greatest rate of reaction, would be the powdered zinc, the greatest surface area, with the highest concentration of acid, the one that contains the most particles, at the highest temperature, where the particles are able to move the fastest. All right, I hope that helps. Please feel free to email me with any questions. Go look at that summary sheet and then try the Google form that I posted along with this assignment. All right, hope I see you all soon. Bye-bye, everybody.